hopefully it's working. Okay, so beam deflection. Let's go to the, oh wow, that's gonna get in the way. All right, beam deflection. So this is the last topic in beams, and like I was saying, it won't be on exam 2. Exam 2 will end with the beam design or the beam selection. Beam deflection, the stuff we're covering today and tomorrow, will be on exam 3. Exam 3, by the way, is a cumulative exam, so it'll have questions all the way back to the beginning where it's just axial stress or resultants and 2D concurrent forces and things like that. There aren't too many new topics once we finish the beam deflection. There's the torque, the twisting type topics, but they're pretty sparse. A lot of your time gets spent on the truss project and things like that. So this beam deflection actually ends up on exam 3. And what we're talking about here is, let's say that you have a cantilever beam. And let's just make a really simple one. I'm not going to do anything with this one. I'm just going to show you. Cantilever, it's got a point load on the end, and we know that, you push hard enough and it's going to do something like that. And beam deflection helps us figure out, what is this delta that it deflected. And maybe it's the delta maximum, like I've drawn there, or maybe it's the delta at any point on the beam. So we'll actually have an equation for this line. Equation of the elastic curve. So we do make some assumptions in there. The elastic curve, so it stays in the elastic region, so that we haven't permanently deformed anything. Once we start yielding the beam, then these equations kind of break down a little bit because they depend on modulus of elasticity, which is not linear outside of that elastic region. So we do assume, and I've greatly exaggerated the amount of deflection there for this little cantilever beam. That probably would be a yielding condition if it deflected that much, probably, depending on the material. And most of these materials, if it's a beam of a structural nature, it's probably steel. So that's not going to bend like that. So how we're going to go about today, we're going to look at, how this stuff works from a theoretical sense and how you can develop any equation of the elastic curve. This would be something like y of x, the y component of any one of these x coordinates, if x is maybe doing this, then we could actually plot the deformed shape of this beam. So how do we develop that? And that's one way. We'll go through a theoretical approach to get to there. And then tomorrow we'll look at assuming you know that. So assuming that someone has already gone through most of the standard types of loads, which I just pulled up a sheet right here. Maybe somebody's already gone through, there's a cantilever beam with a point load on it, the very first thing. And they've already, they call it deflection at any section in terms of x is what I call the equation of the elastic curve. And they've already done that. So, you could just go and take that equation. Or if you want to know just the maximum deflection, you could just take that equation as long as you know what these variables to plug in are. And they tell you over here in the little diagram what the variables are. So how do you get to that? And how do you deal with it when this isn't exactly what you have? Maybe you have a cantilever beam that has a point load and a distributed load on it. How do you deal with that? And so that'll be mostly tomorrow. We'll look at we'll just do this cantilever later on today, but we'll look at how do you get to that equation to begin with from a theoretical kind of point of view. So what you would do, one way to think about it, maybe there's other ways, but one way to think about it would be, let's take a beam, a simply supported beam. So it doesn't have to be simply supported. I just want to do it this way. and you put a load on it in the middle or somewhere. It doesn't have to be the middle. Again, I'm just trying to make it symmetric and easy to deal with. We're not going to look at numbers here. This is going to be variables. And then you push hard enough and, you know, it'll deflect. And again, that's way exaggerated from what it would really deflect. But if we took a little piece of it and kind of blow that piece up and exaggerate the amount of deflection. So, you know, something like this. This is ridiculously exaggerated for that little piece of the beam. We've already looked at somewhere in there, there's a neutral axis. You know, it's having to make this curve shape. And above, the way I drew it, above this neutral axis, there's compression, below it, there's tension. And so there's changes in length above and below the neutral axis. So that means there's strain. So if I've stretched it or compressed it, then it has some amount of strain in it. And if I define some variables here, so let's say that, you know, I make a arc here and say that's angle theta, and say that, let's use blue. This distance, we'll call that, probably should call it this guy, capital R. It's a radius. So had I drawn this nice and like circular or whatever, it would look more like a sector out of a circle. And this R might be something that I call radius of curvature. And if I go outside of beams and just reference other sources of curvature and lines of curvature and things like that, there are equations for curvature and radius of curvature. Yeah, those are not the same word, by the way. So curvature is actually a lot of times it's this curvy K type thing, and it usually equals 1 over, or well, not usually, it does equal 1 over the radius of curvature. So radius of curvature and curvature are reciprocals of one another. And so what I've kind of labeled here would be the radius of curvature. It looks like a radius from this center point up here, and that's kind of what I'm dealing with here. So I know from previous bits of information not related to necessarily statics, but maybe physics or geometry or whatever, I know that curvature, this K, is equal to this thing. Actually, this is backwards. This would be R. R is going to equal this. Radius of curvature equals this. Curvature would be the reciprocal of this. So that does not particularly look useful. You know, it looks like, okay, that's great and all, but what am I going to do with this? So again, curvature would be the reciprocal of this thing. And I can take this would be, if I just had a line that was curved at some radius, then this would describe that line. Or this would describe the radius of curvature associated with that line. And then I can apply that idea to a beam. So again, a beam in use is probably not going to curve that much. You know, it's not nearly the amount of curve that I've drawn. You certainly normally don't want your buildings to be wobbly like that. You want them to be pretty orthogonal. And so if I make that assumption, that's pretty valid. I don't want my beams or whatever I have in my machine that looks like a beam, I don't want them to bend that much. Then I can take this equation and notice right here, dy dx, I know what dy dx is, that's slope. And in this case, that means if I were to draw the, you know, the beam as it's bent, then at any point, let's just pick this point, you know, that's the slope of the thing, right? So that's dy dx, rise over run for some point. So it's the slope of a tangent line. And if I know that I want the slope of the tangent line to be pretty small, you know, it can have some deflection, but not a whole lot of deflection. You know, in the real drawing, this thing, you know, this is and even exaggerated probably. And when I draw the slope there, it's pretty horizontal, right? It's a small slope. I don't want a whole lot of deflection in these beams. And when I make that dy dx is small, so a small number, and I put a small number in here, then I square the small number compared to 1, so 1 plus a really small number squared is pretty much 1. You know, we're talking about a very small radian measurement here for this slope. I square that small number, make it even smaller, add it to 1, that term is pretty close to 1. Then I raise 1 point whatever 0000 number I have, raise it to the 3/2 power, it's pretty much just 1. So once I make this assumption that for beams in bending, dy dx is small, then this equation says that the denominator basically is just 1. So the radius of curvature is really close to just the numerator, which is this second order derivative. And that's not so bad, as long as I have some equation to deal with there. So I need to figure out what equation actually goes in there. But what I can do with that is, if I take the integral of the second order, then I'll get dy dx, right? So the integral of this thing, d squared y over dx squared, the integral of that would be dy dx. So if I integrate that equation, I get the slope. So that's useful. I would know the slope of any point of my deflection as a function of x. If I integrate the slope, so I'm integrating dy dx, then I just get y, which is the displacement, which is what I want. So I can generate the equation of the elastic curve. So I can actually generate an equation y of x if I integrate this radius of curvature twice. I just need to know what to put in for the second order derivative to integrate to begin with. You know, I can't just integrate this thing. I have to have an equation in there. So going back to this thing, what I can do here is, I said earlier that the neutral axis is not strained. There's no stress, there's no strain on the neutral axis, but above and below it, there is stress and strain. In particular, strain is interesting at this point because strain is related to changes in length, and I know the length of the neutral axis. So length of neutral axis from this drawing, again, really exaggerated, would equal, it's an arc length, so it would equal this radius of curvature times theta. Theta's in radians, and I would have, that's just an arc length, is all that is. And so that's the arc length of the blue dotted line. And then I could pick some other line. Let's make a red dotted line. I'm just picking a random one. The length of this line is also an arc length, and it would be the distance from the same reference, but I've got to measure down to here. So I'm going to call that one the radius of curvature plus some amount y. So some distance from the, you know, basically this little distance is what I'm calling y. So the length of that thing, length of, we'll just call it the other line, would equal its radius, r plus y, times that same theta, so that's another arc length. And now I've got two different lines, and I can calculate basically the strain way back in the beginning, strain was the change in length over the original length. So originally my red line, before I loaded this thing up and deflected it, bent it, the red line was the same length as the neutral axis because they were, horizontal parallel to each other. And then I deformed it and made it into this curve, and now it's got a new length. So the change in length would be the length of the other line, which I've got as radius of curvature plus y times theta, that's its arc length, minus the original length it was, which was just radius of curvature times theta, that was the length of the neutral axis, divided by the original length, which would just be r theta. That would be strain. And if I expand this, r theta times y theta, not times, plus y theta minus r theta over r theta, I got r theta minus r theta, so those go away. Then I've got y theta over r theta, those go away. And I've got that the strain is this distance y, whatever it happens to be, over that radius of curvature. And we haven't talked about it a whole lot, but in general, in these flexural stress equations, whenever we want to do the maximum stress, maximum strain, or whatever, for max values, y equals c. And so c is just defined to be the largest distance from the neutral axis in flexural stress. So for instance, if you wanted to do sigma equals negative m times y over I, you could say sigma max equals m times c over I, and c is the largest value possible for y. So remember, like in a T-beam, the neutral axis is kind of shoved up towards the top of the beam. So the distance from the neutral axis to the very bottom of the stem in a T-shaped beam, that's the number you would use for y, and you just kind of call it c. Yeah? Ooh. Yeah. It's just the, because I wrote it wrong. This is an x. Yeah. Yeah, you wouldn't do dy, that would be kind of, I don't even know what that would be. So yeah, I wrote it wrong the first time. This one's actually right. That one was wrong. So C is just a way to say that, hey, just go find the largest value you can put for y, put that in there, and that would also apply here, where we could say that, well, the maximum strain, that's an epsilon, is equal to C over this radius of curvature. Okay, and I could take that bit of information and a few other things, including this equation. And if you remember, it was the first week or so, if you remember how you relate these two, sigma max, maximum strain, so how in general, not necessarily the maximum, but how in general you relate stress to strain, it was Hooke's law. And Hooke's law said that in this scenario, when we're talking about tensile strain, sigma equals E, the modulus of elasticity, times epsilon. So I can take sigma, plug in here. I can take epsilon, plug in here, and then my equation looks like this. M times C over I. I've dropped the negative sign, this negative sign, I've dropped it off here. Remember that negative sign is in the original equation to help me distinguish tension and compression, but once you do C, you're just using the largest value, so it may or may not be tension or compression. So you have to figure out if it's tension or compression based on the direction the beam is bending. So that's why I didn't put a negative sign in there. MC over I for sigma, modulus of elasticity, and this C over radius of curvature. And now I can rearrange this thing a little bit and end up with basically, also remember this guy, R is that second order derivative. Right now we'll leave it as R, but eventually we'll sub in that value. And you would end up with, let's just do R. So move R over, and I would have M well, do I want to move it over? Actually, I think I want to move the E over. The C's cancel each other out. And hold on a second. Yeah. M over E, I. C's cancel each other out equals 1 over rho, or not rho, R. In this previous time I wrote it as rho, but not actually rho. And oh wait, did that backwards. That is, this equation is actually 1 over R. I'll have to fix that. 1 over R, and which is that curvature, right? So that equation is actually the curvature equation, which is 1 over R. That's what was messing me up. 1 over R would be the second order derivative, which is what I have right here. So what I have then, this moment, now the way I generated this beam, this flex here, this nice curve, is I just put one force on here, P or whatever it might be. What we've developed here would be the equation of the elastic curve for a given bending moment. So remember last week, or maybe it was 2 weeks ago, you were doing the thing where you develop an equation for m of x at any point in a beam. So every time m of x would change, the equation for m, then you would also need to change it here. So this is, a function. The bending moment is not constant in the beam, it's changing. And there are sections in the beam where the equation is constant, but then as soon as you add a point load, or you add a concentrated moment, or you add a distributed load, then that changes the equation m of x. So you would actually have to develop a piecewise function. Say you had a beam, cantilever beam, but it has a point load and a distributed load on it and no load in between them, then you would have to develop a bending moment equation for both of these sections of the beam. So you'd have one section, section A, where there's one equation for m of x, and then section B over here would have a different equation for m of x. So every time your bending moment equation, m of x, changes, you'd have to write another one of these. You have to figure out another equation of the elastic curve. So basically it would change each section. The one we did with a point load on the end of the cantilever or a single point load in the middle of a simply supported beam, then you could take advantage of symmetry or the fact in the cantilever that there's just one load and not have to write a new equation. Technically, the cantilever, the simply supported beam would need two different equations, one for the left-hand side of the point load and one for the beam on the right-hand side of the point load. The thing is that they would be symmetric. They would, the shape of the beam, if that point load's in the middle of the beam, the center of the beam, center of the span of the beam, then it would be the same equation on either side, just in reverse. So those you wouldn't have to develop a separate equation for every section, but something like this one, you would have to have two different equations that you put together piecewise in order to create the entire equation of the elastic curve. But what this does for me is it says that I have a way to do this now. So I can start integrating this equation. I just need an equation to put for m of x, which we've done. So let's go back to our cantilever beam with a single point load, just to make it doable for an easy deal. Let's put variables on it instead of numbers for now, so that we can see the variables in the equation. You know, we might want to, it doesn't particularly matter, but let's actually, since I did it this way the other time, let's make x go from to the left. So x is positive going to the left. This is x equals 0, and this would be x equals L, the length of the beam. So the length of the beam is just going to be L. That's similar, I think, on this one that I downloaded. Oh, it's messing with me. Here, they have a lowercase l for the length of the beam. They actually do have x at the wall, so it might generate a slightly different equation than this one, but we'll do it this way. All right, so how we would do this is first we need something to put in for m of x, otherwise we just have to write the integral of m of x. So we do that by cutting the beam open, drawing a free body diagram. It has point load P. I said that x is going to go this way, so x equals 0 and x equals x out that way. Got a shear force, and there's m of x that I'm interested in. There's v of x, which I'm not particularly interested in for this equation. Maybe there's some other reason I would want to know that, but not for the bending of the beam. Then I can go in with my free body diagram and say that I can do the summation of moments about this cut surface that I cut through. We'll say clockwise is positive. And this would tell me that P times whatever value I put in there for x is going to add to the moment at x and equal 0. So that way I have an equation for m of x that says m of x equals negative p times x. It's just the opposite of p times x. Remember, when I do these beams and bending, a lot of times we don't use this side of the beam, we use the other side, but you have to remember the correct orientation for those internal bending moment and shear forces. Otherwise, your equations will have the wrong positive and negative signs on them and things like that. So if we draw this side of the free body diagram, the bending moment is going clockwise, shear force is going down. Actually, shear force goes up, not down. I drew it going down, but it needs to go that way. All right. So now that I have an equation for the bending moment in this beam, and that equation would be good from the wall all the way to the point load. There would be no need to have a different bending moment equation. I can take negative p times x, plug it into what we just sorted out. So instead of m of x, we'll write negative p times x. The denominator was e times I. That was just the modulus of elasticity and the moment of inertia of the beam, both of which we think would make sense to have in an equation that's going to tell us about how the beam bends. The modulus tells us, you know, is this beam stiff or not? The moment of inertia tells us how rigid it is compared to wanting to bend. So a large moment of inertia would make it not want to bend very much. Those take care of the material. E takes care of the material, and I takes care of the geometry. Is it a L beam or a C beam or a T or an I or whatever it is, and that's all summed up in that moment of inertia. So those two, which would affect how the beam bends, are constants in the equation. And so now what I would want to do is, this doesn't, that second order derivative is not actually the thing I want. I either want the slope, and what I really want is an equation for y. So to get that, I need to integrate both sides. So integrating the left-hand side just gets me down to dy dx. And, well, I'm in, just so you are for sure, I'm integrating with respect to x because, that's my horizontal variable. I want to have this equation valid from the left end of the beam all the way to the wall. So x is the variable I want to integrate over. So the second order derivative just becomes the first order derivative, dy dx, which is the slope, which sometimes you might just call theta of x. So it will be the slope of a tangent line at x, and it'll come out in radians. It won't be degrees, it'll be radians if you actually plug numbers in and solve for it. And then I just need to integrate the other side. So I have to integrate negative px over ei times dx. So like I said, e and I are constants. They're a material constant and a geometric constant. And I assume that the beam does not change materials from one end to the other. So E doesn't change. And I assume that I, the moment of inertia, doesn't change from one end of the beam to the other, which are pretty valid assumptions. I shouldn't have to worry with them changing from one end to the other. So when I do this, I basically end up integrating negative px. I can take the 1 over ei outside, and I could take the negative out also, I suppose. I just left it in there. So that's a simple integral to integrate. And I would end up with 1 over ei times, well, how about we take, for now, the ei and move it over. So it's over here. Since it's constant, we'll just leave it over there by itself. So we'll move it over to the left-hand side. It's actually with the theta, just to get it out of the way, and do the integral of negative px dx. So negative px squared over 2. And I actually want to integrate this from, x equals 0 to x equals L. So when I integrate this, I generate some constant of integration. There's some boundary condition that I have to figure out what to do with. And when I plug in 0 for x, then the thing goes away. When I plug in L, then x becomes L. So I can have ei times the slope equals negative p times L squared over 2 plus this constant of integration that I've got to figure out what it is. And theta is the slope, right? And looking at my beam up here at the wall where x equals L, I can be pretty sure that the slope there is horizontal. So, at the very wall, assuming the beam was horizontal to start with. So assuming the beam was horizontal to start with, which is what I meant to imply here with the picture, is that at x equals L, the slope should be 0. So at x equals L, slope equals 0, horizontal. And so I plug in theta of x, or theta of L in this case, as 0, so that left-hand side becomes 0. I plug in x equals L here, and well, that's just negative PL squared over 2. And, well, actually, is that what I want to do? plus C1. Therefore, C1 has to equal PL squared over 2. Then my equation, EI times the slope equals negative P x squared over 2 plus C1, which is PL squared over 2. I kind of plugged this L in a little early, so when I wrote it down, before I told you that I was going to put set x equal to L. All right. This is useful if I want to have an equation for the slope of the thing, because I could just move the EI back over to the right-hand side, divide the right-hand side by EI, and then I have an equation for dy dx. And a lot of times you're given that. So in a chart like we had right here, you do have, no, here you go. You have an equation, PL squared over 2EI for theta. So that theta would be dy dx, dy over dx. PL, their lowercase l is the same as our uppercase L. And it's squared because when you plug in the x equals L, then you would have two of those L's. They also give you the maximum delta. No, they don't give you the maximum slope. Actually, this is the technically it's not called the maximum slope. It's the slope at the free end. Sometimes that doesn't make sense on some of these. These are all cantilevers, I guess. Okay, when they're simply supported beams, then sometimes they'll give you the slope at either end of the beam, because it might be different if there's a point load in a cantilever beam and in a simply supported beam that's off center. They might have different slopes. Looks like these are all cantilever beams though, so they're giving you the slope at the free end, which is the maximum deflection. So this PL squared over 2EI would be the maximum value for us. And for us, we developed this equation where the free end is x equals 0. So if you put x equals 0 in here, you would get PL squared over 2EI. So we would get the same equation that they derived. So we could have that if we wanted it. And sometimes it's useful because sometimes one of your failure criteria is that the beam can't deflect a certain amount. And so that would be one of the things that you would have to check. If it's not breaking or yielding, it might still deflect too much. And so you might have to know the slope at these maximum points, or maybe the slope at any point. Our equation generates the slope at any point. The ones that are usually in the charts generate the slope that's maximum or at the end or something like that. But again, most of the time what you want is actually that deflection. Sometimes the slope matters, like if this is a shaft that has gears on it and bearings and things like that, they can come out of alignment if they slope too much, if there's too much slope on them. And that would be a thing that you would have to deal with in that kind of scenario, is how much slope do you have, and can these bearings or gears, teeth tolerate that kind of misalignment? But usually what we want to know is the function for y. So we have, let's go back to writing this one, EI dy dx equals all this stuff. And to get y out of here, we need to integrate again. So if I integrate the left hand, again, I'm integrating with respect to dx on both of these. So the left-hand side, now I have, I still have E and I as constant. I've kind of keeping them over there just so they're not messing with the more difficult thing to integrate, although in this case it's not particularly hard to integrate. And then there's y of x. So that's my equation of the elastic curve. I just have to integrate this px squared over 2 plus pl squared over 2. So when I do that, I would get, still have the negative in there, so negative p, now it's x cubed over 6 And then the PL squared over 2 is just going to have, plus PL squared over 2 times x. And I generate a new constant of integration. I called that other one C1, I think. Yeah, so this will be C2. And here I can do a similar thing. So I need to look for a known condition. And looking back at my original picture, I said that at the wall where I set up x equal to L, you might have set x equals 0 at the wall. You know, a lot of times that would be how you would normally do it. I just did it this way so that our equations would match. But x equals L, then it shouldn't have any deflection. There should be y of x equals 0 at the wall, so that it's not deflected up or down. We're assuming it's perfectly attached to the wall, and it doesn't have a way to move there. The other end, x equals 0, the way I drew it, that one is the one that's going to have the maximum deflection. So I can do a similar thing where I say that, well, I know that at the wall, the way I set it up, x equals L, the length of the beam, and at that point, y of x equals 0. So again, a similar thing happens where the left-hand side just zeroes out. And then I've got to put L's in everywhere I have x, so negative P L cubed over 6 plus P L squared times L, so that's P L cubed over 2. There's C2, and I can combine these together, so I could multiply both of these by 3, so I can add them. And I have negative PL cubed over 6 plus 3 PL cubed over 6. So that'll give me 2 PL cubed over 6. And then 2 over 6 is just 1/3. So we can simplify that a little bit. And C2 would move over to the other side, or well, it's positive on this side. We'll move the PL cubed to the other side. So C2 is plus C2. C2 is equal to negative PL cubed over 3. And then I can put that back into my equation. Y of x, currently it's still multiplied times EI, equals negative PX cubed over 6 plus PL squared times x over, what was that, over 2? Plus C2, which is minus PL cubed over 3. And there's a lot of common terms in there. I've got some things I can add together. I can simplify it a little bit and move that EI back to the right-hand side because it probably doesn't need to go with the y of x. And I could end up with y of x is equal to, take out the common stuff, P, we'll put E, I, the common denominator among all that stuff is 6, and then figure out what would be in each section of this. So negative x cubed, 3L squared x, and this one we need negative 2L cubed. That equation, if I were to plot it, would give me the actual shape of my cantilever beam. And I don't know if it's the exact same form that is in this little guy or not. Let's see. No, they have it simplified a different way. Actually, oh, you know what? Because they're measuring from x equals 0 at the wall, so they ended up with a little bit different setup. You do have to use the same coordinates. So this equation that we developed sets x equals 0 at the free end of the beam. So it's not going to look the same as the one in the chart where they set up x equals 0 at the wall. So we could have done a similar approach and matched what the that particular chart had, but x would equal 0 at the wall, which would change our boundary conditions. So instead of x equals L, y equals 0, we'd have x equals 0, y equals 0, x equals 0, theta equals 0. And that would have changed our how we evaluated the constants a little bit, and therefore changed this. So this equation is good as long as x equals L at the wall, x equals 0 at the free end. And the other thing that it would also do is, I guess we didn't actually ever set if y was positive, up or down. I don't guess we ever set that, and it doesn't show up here. But if you notice on the charts that you get, normally they have a direction. It's off the edge, so I can't see it. There it is. Y is positive when it goes down. I don't know why well, it's just really small and blurry. So you would get positive values for y using their equation anyway, but it would be downward deflections, which is normal. You normally have downward deflections. This chart does have, here's some simply supported beams, and you get similar stuff. So let me zoom back out a little bit. You get the equation of the elastic curve, you get the maximum deflection, you get, in this case, two different thetas, but they're both the same value because this one is showing you a cantilever. I'm looking at let's make it the top one. So the top one here, it's a simply supported beam, point load in the middle, so you expect the deflection on the left-hand side of the point load to be the same as the right-hand side, just mirrored. This next one, number 7 here, the point load is off-center, so you get two different equations for the theta at the one end of the beam versus the other end of the beam. And you get two equations of the elastic curve here because the beam is not making a symmetric type deflection on either side of the point load, so you would need two different equations, and they give you both of them. They also give you two different things here. So one of them is the maximum deflection, and the other one is the deflection at the center of the beam. So that just is, a lot of times you're interested in the deflection at the center of the beam, whether or not it's the maximum deflection, so that one gives you that piece of information. There's one with a distributed load. Here's one with a concentrated moment on one end. So notice you don't have one where the concentrated moment's on the left end. You have to mentally flip this thing over, mirror it, and mirror all the variables so that you're calculating if you want the moment on the left end of the beam versus the right end of the beam. This particular chart also has some that have unevenly distributed loads on it. We're not going to deal with those, but obviously there are those available. This is a pretty common looking chart. One thing about these charts is that they only ever, that I've seen, show a single load on a beam. So a single point load not at the end, single distributed load, so forth. What we'll do next time is, all right, that's fine, but how do you deal with a beam that has more than one load on it? Because you have to combine these somehow. And it's pretty simple. You can literally add them together. You could take the equations of the elastic curve and add them together. And so we'll do that. There are some times when you have to be a little sneaky on how to generate a set of equations for a condition that doesn't really match any of these, but you can deal with that. And I'll show you 2 or 3 of the ways to deal with that. Let's see. I think that is all we need to do from here. I'm not going to ask you on an exam anyway to go and generate one of these equations. One of these y of x. You may have to generate an m of x possibly, or not generate the equation, but use the idea of how to get the bending moment at any point in the beam without drawing the shear and bending diagram. But I'm not going to, and again, this is test 3 anyway, but I'm not going to ask you to figure out this, how do you calculate this equation for the elastic curve. I'm not going to ask you to do that on the exam because can be a little lengthy, and unless I ask you a super simple one like point load on the end of a beam, then it starts to become a piecewise thing that you have to do multiple little sections and add them all together to create a function. Okay, so that's just where this idea of beam deflection comes from, some of the limitations of what you're dealing with, how this kind of information is generated. Most of the time, if you're dealing beam deflection, this is where you'll start. You'll start with one of these. You just need to know when these equations work, when they don't work, how to combine them together. And if you know a little bit of how those equations were generated, then that'll help you know when you can put them together and do stuff with them. So we'll do that next time. We'll actually combine some of these and start with the chart, not deriving the equation, but someone else has already done that for us. And how do we use that? Any questions about that? No? All right. I think we're good for today.